Hello and good morning, everyone. I welcome you all to Unacademy, India's largest e-learning platform, and I welcome you all to my session of Antennas Maha Marathon 14. I welcome you all to our channel of Gate Conqueror. How are you all, dear? Just confirm the video and audio. Just confirm the video and audio once. Good morning, Anil, Chandni, good morning. Glad to meet you. Hello, sir. Good morning, good morning, good morning. Yes, JK, good morning. Yeah, fine. So let us start the session of Antennas Maha Marathon 14. Before we start, let me introduce myself. I'm GC Reddy, Security AR 1931. I worked as a motivational speaker pan India for the past 12 years, an expert in field theory and communications. As you know, this is a channel, Gate Conqueror, and this is a Telegram link for the same. You can just take the screenshot of this and you can join us on Telegram. This is where you can access all the Gate Conqueror faculty. So we'll start up with the Antennas Maha Marathon 14. As you know, this is the Antennas Maha Marathon series. Is intended to cover just a second here. Yeah. Okay. This particular series is intended to cover maximum concepts of antennas. Antennas Maha Marathon series, as you know, we had covered all the concepts of antennas, starting from the monopole antenna, moving up to dipole antennas, basic mechanism of antennas, antenna parameters. We had covered everything related to antennas, like antenna arrays, 2-element, 10-element arrays, and the 7 sister antennas, antenna measurements, resonant, non-resonant antennas. We had covered everything regarding antennas. And in wave propagation, we had covered the principal modes of propagation, which are ground wave propagation, sky wave propagation, and space wave propagation. And in special modes of propagation, we had covered scatter propagation, which are tropospheric scatter and ionospheric scatter, and we had covered duct propagation. And also we had seen the structure of atmosphere. And in the previous session, we had also derived the refractive index of ionosphere. We had also covered the refractive index of ionosphere. We had derived mu or n, the refractive index of ionosphere, which is sin I by sin r, which is equal to under root of 1 minus 81 n by f square. This is what we had covered. in our previous sessions. Any doubts so far you can ask so that we can move forward. Both clear, very good, very good. Yes, sir. Yes, sir. Clear, 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 very good. So ask everyone to join very, very soon, dear. We are going to start, we are going to move up after the refractive index of ionosphere. We are going to understand how the waves will bend in ionosphere, and also we'll see the concepts like critical frequency, maximum usable frequency, least usable frequency, optimal working frequency. So this kind of important concepts we'll try to discuss in this particular session, along with ionospheric abnormalities. So ask everyone to join very, very soon, dear. This is going to be a very important session for you all. So you can see here, this is what we had covered in the previous sessions. We had seen the principal modes of propagation. In principal modes of propagation, we had covered ground wave propagation, also called as surface wave propagation or Norton surface wave propagation, where the frequency range is up to 2 megahertz. And we had covered the sky wave propagation, also called as ionospheric propagation, where it uses ionosphere. Frequency range is between 2 megahertz and 30 megahertz. And also we had covered the space wave propagation or the line of sight propagation, which is between 30 megahertz and 300 megahertz. And also we had seen the special modes of propagation. Under special modes of propagation, we had completed scatter propagation. In scatter propagation, we had seen ionospheric scatter and tropospheric scatter. And we had covered duct propagation. And also we had seen the structure of atmosphere, in which we had seen the structure of troposphere and structure of ionosphere. In the previous session, as I told you, we had covered refractive index of ionosphere. The refractive index of ionosphere, we got it as I told you, mu. We had derived the value for mu or n, which we got it as mu or n is from Snell's law, sin I by sin r, which is equal to under root of 1 minus 81 n by f square. Now we'll further try to derive the concepts related to the refractive index of ionosphere. Okay, voice is low. Okay, fine. Okay, voice is low. Now, Bhaskar and others, now can you check the voice once? Is it okay now? Just check once and let me know. Is it okay now? Yeah, it seems to be okay. Oh, fine. Oh, fine. Thank you. Thank you. Yes, yes, correct. Now we'll go for the mechanism of radio waves. Mechanism of radio waves bending by the ionosphere. How radio waves are bent by the ionosphere, that's a concept. How radio waves are bent by the ionosphere. So listen carefully, dear. Very important concept. It's curvature of the Earth's surface. There's a curvature of the Earth's surface. This is the ionosphere. As you know, it starts with which layer? Ionosphere starts with the D layer or the D region. This is the D region starting at 50 kilometers. Major layers are D, E and F. Okay. So this is the E layer and this is the F layer, which is further split into F1 and F2. So these are the different layers which will span from 50 kilometers to 400 kilometers. Now, let me take a transmitting antenna. And a receiving antenna. Now the wave is sent upwards like this. It will reach back like this. Now, this ionosphere at different heights, they have different ionic densities and thereby they have refractive index. So the refractive index of ionosphere, as we have derived, which was given by what? N. Refractive index of ionosphere, which is given as N or mu, is under root of 1 minus 81 N by F square. Okay. Now, refractive index N, this has a tendency that as you move up, let me consider different regions. Listen very carefully, dear. It's very, very important. If you understand this topic, the next 5 or 6 topics will become very easy for you. Vice versa is also true. So you should be very careful, okay? Now, these are the different regions. Let the refractive index is given by N1, N2, N3, N4, N5, N6. And as you know, already we have discussed, this N value will be far greater than 1 when it is very close to the Earth's surface. As you move up, it decreases. So as you are moving up, what happens to N? N decreases. Means N1 is greater than, N2 is greater than, N3 is greater than, N4 is greater than, N5 is greater than, N6. As you are moving up, the value of N decreasing. Am I right? Is that clear? Everyone, please let me know. Is that clear? So as you move up, N decreases. Now, N is decreasing. It means what? What is happening to the ionic density? The ionic density is given by capital N. For this N1, the ionic density is capital N1. For N2, capital N2, so on. Ionic densities are N1, N2, N3, capital N4, N5 and N6. And as you are moving up, what is happened to the ionic density? It is increasing. That means what? N1 is less than, N2 is less than, N3 is less than, N4 is less than, N5 is less than, N6. As you are moving up, the ionic density is increasing, refractive index is decreasing. Just everyone tell me, is that clear up to this point? Why I am asking again and again is because there is a hidden concept here that you need to understand. You need to understand it very clearly, dear. If you understand this concept clearly, the rest of the derivations will become very, very simple. So the refractive index NR mu is given by this, and the wave is sent upwards towards the sky, towards the ionosphere, and once the wave has entered the ionosphere point, it has started bending, it is getting refracted with these layers and it is starting bending. It has started bending due to the continuous refraction. It has started bending, and at one point, what is the amount of refraction here? The refraction angle is 90 degrees. At this point, the wave will start to come down. Now you tell me at this point, how much is n value? Out of the available n values, can I say at the maximum value? That means you compare n value here, n1, n2, n3, n4, n5. When you compare the n values here, in comparison with the previous n values, the n value here or the capital N value, ionic density value, is it maximum or minimum? How is the ionic density? Is it maximum or minimum? How is the ionic density? N, capital N value. Is it maximum or minimum? Just a second. Maximum, very good. Okay. So, this ionic density value at this point is maximum. So, refractive index mu is equal to sin I by sin R under root of 1 minus 81 n max by f square. Can I say this? Because whenever the wave is bending back by the ionosphere, at that point, by default, the value of n is maximum. Can I say this? It can be any point, but at the point of reflection, always the n value is maximum. We can say in this way, I'm right. And you tell me what is the angle of refraction. At the point from where it is coming back or bending back, at that point R is always 90 degrees. The angle of refraction is always 90 degrees. And N is always maximum. So I'm going to confirm two conditions. At the point when the wave is coming back, always N is N max. Angle of refraction is always 90 degrees. So can I confirm these two conditions? N refractive index or mu is sin I by sin R. It's under root of 1 minus 81 N by F square. At the point of refraction, you can say the point of reflection, angle of refraction is 90 degrees. N is N max. N is N max. So I can say N or mu is equal to sin I, angle of incidence. Sin R is sin 91 is under root of 1 minus 81 N max by F square. Is that clear? Next we go for critical frequency. Next is critical frequency given by FC. Sorry. Critical frequency is defined as maximum frequency that can be reflected back by the ionosphere at vertical incidence. At vertical incidence. This is one definition. Can anyone tell me what is vertical incidence? Can anyone tell me what is vertical incidence? The second definition, it is the minimum frequency that can be reflected back by the ionosphere at non-vertical incidence. Now the question is, what do you mean by vertical incidence? Vertical incidence refers to incident angle is 0. When you are sending the wave vertically upwards like this, the angle made with the normal is 0. See the angle between these 2 points here. The wave is sent like this. Then this is the angle, V shape. If it is sent like this, this is the angle, more angle. The moment I am trying to straighten up, this index finger is showing you the incidence. The moment I am trying to straighten up, the angle is decreasing. At vertical incidence, angle is 0. That is called vertical incidence. Incident angle is 0 degrees. Now, why you got these formulae or these definitions in this way? For that, let me analyze the formulae of refractive index of ionosphere. N or mu is equal to sin I by sin R is equal to under root of 1 minus 81 n by f square. Okay, 1 second here, sorry. Okay, fine. So under root of 1 minus 81 n by f square. Trying to substitute the conditions. The wave needs to come back. What should be the angle of refraction? 90 degrees. How much should be n value? What is the n value at the point from where it is coming back? N is n max. That's why this is very important. How you got these two conditions? From the previous derivation. From this one. That's why understanding mechanism of radio waves bending by the ionosphere is very, very important. N is n max. For critical frequency calculation, incident angle is 0. F is equal to Fc. F is equal to Fc. Substituting N or mu is equal to sin 0, 0 by sin 91 is under root of 1 minus 81 n max by Fc square implies 1 minus 81 n max by Fc square is 0 implies 81 n max by Fc square is equal to 1. Fc square is 81 n max. Fc is 9 root n max. Fc is the critical frequency measured in megahertz. And max is ionic density measured in per meter cube. Got it? Is that clear? So that's the formulae for critical frequency. Fc is equal to 9 root n max. So what can I say? Critical frequency is defined as the maximum frequency that can be reflected back by the ionosphere at vertical incidence, are defined as the minimum frequency that can be reflected back by the ionosphere at a non-vertical incidence. You'll get more and more clarity as we move forward and do some more derivations, and we'll do some more analysis. Okay? Next is virtual height. See the why virtual height is important. Let me explain first. See, I'll tell you a scenario. This is Earth's surface. This is where ionosphere is starting at 50 kilometers. Ending up at 400 kilometers. Now you are sending the wave towards ionosphere. These are the layers. The ionosphere. These are layers in the ionosphere. Transmitting antenna, the receiving antenna, the wave is sent up, it entered ionosphere, got refracted continuously, and at a point where n is n max, it came back. Already I told you this particular scenario. Now the problem is, if you are watching from this point, can you guess at what point it is coming back? Please respond, everyone. If you are watching from this point, can you guess at exactly at what point it is coming back? Yes, Bhaskar, yesterday you missed. Yesterday, I think roughly we took some 3-hour session. Approximately, I don't remember exactly, but approximately we took some 3-hour session yesterday. You can just go through, okay? You can just go through that. We took some 3-hour session yesterday also. Yes, dear, please tell me, if you're watching from the transmitter point of view, can you guess at what point the wave is coming back? This height up to which the wave has been propagated, from this point the wave is coming back. This height is called actual height. This is actual height given by h. This is the actual height up to which the wave has went or penetrated into the ionosphere before coming back to the receiver point. But my question is it possible for us to guess exactly at what point it is coming back? Bhaskar, got my question? Is it possible for us to guess that at exactly at what point it has started to come back? No, dear, no. See, no, Bhaskar, no. No. What I am trying to tell is, see, Bhaskar, we had sent the wave vertically upward, we had sent the wave upward into the ionosphere. As the moment the wave has entered the ionosphere, it has started bending. Now my question is, do you know exactly at what point it will start coming back? So if you know that, you'll understand the actual height. Can you predict at what point it will come back exactly? This fellow is penetrating, Bhaskar. We cannot predict at what point exactly it will come back. That's why Nmax, it's okay. But we don't know, no. Height, I'm asking about height. I'm asking about the height. This point, can you predict this point? Yes, we cannot predict the height. That's the problem. So what we do is, we'll send the wave vertically upward. We'll not send it from this point, but we'll send it from this point. We'll send an impulse signal vertically upward like this. And we'll see when it is coming back. Now there is no trajectory. Directly vertically upward we are sending. And what we are doing is, now as Bhaskar said, velocity with which the wave is being sent. Velocity. What is the velocity with which the wave is being sent? See, velocity of light. 3 into 10 power 8 meter per second. The velocity with which the wave is sent, or the wave is moving. Now you are sending it vertically upwards. The wave will go at some point and come back. You note down after how much time it is coming back. Let the time is t. What is t here? Two-way travel time. Time taken by the wave to reach up to this point and come back also. The total time is t, two-way travel time. how much will be the time if t is a two-way travel time? For example, you had sent it up vertically upwards at 6 a.m. You got the signal back at 6:01. The signal is the signal that you had sent is received back at 6:01. So how much is the time taken for the wave to reach to this point and come back? Example, only example. 1 minute is very big time. For our understanding, I am trying to take that. Okay. So what is the time taken for the wave to travel to this point and come back? 1 minute. How much time it will take to reach to the top? 30 seconds. If t is a two-way travel time, t by 2 is the time taken by the wave to reach the top. Is this clear? Just let me know, is that clear? Just pardon me 1 second, okay? Okay, sorry, heavy cold. Fine. So t by 2 is the time taken to reach the top. Now I want to calculate this distance. Velocity or you can say speed. You can say speed. Distance by time. Distance is now, this distance is now, this is actual height h. This distance is now h prime, virtual height. H prime, distance traveled by time, t by 2. So virtual height is c into t by 2. So this is the formula to calculate virtual height. Now because that actual height calculation is not possible, because that the actual height calculation h is not possible, we will calculate the virtual height, which is h prime. And always virtual height is always greater than the actual height. H prime is always greater than h. In a simple understanding, how do you find h is a projection here. This is for your simple understanding. Okay? Okay, dear, everyone. So that is about the virtual height. So we had completed the derivation for refractive index of ionosphere, n or mu, sin I by sin r, under root of 1 minus 81 n by f square We had also completed the concept of mechanism of radio waves bending by the ionosphere, and also we derived the derivation for the critical frequency, which you got it as 9 root n max Fc is a critical frequency measured in megahertz. Nmax is measured in per meter cube. And critical frequency is defined as the maximum frequency that can be reflected back by the ionosphere at vertical incidence, or a minimum frequency that can be reflected back by the ionosphere at a non-vertical incidence. And also we derived the formulae for calculation of virtual height, as actual height calculation is not possible, which is C into T by 2. Okay, now we'll move on. With maximum usable frequency, MUF. Maximum usable frequency given by FMUF. It is defined as the name indicates, it is defined as the maximum frequency that can be reflected back by the ionosphere at any incidence, at any incident angle. At any incident angle. How to calculate this? N or mu is equal to sin I by sin R under root of 1 minus 81 n by f square. Okay, substitute the conditions. Incident angle, any incident angle not equal to 0. When the wave is bending back, angle of refraction 90 degrees. N is N max. F is FMUF. Substituting, mu is equal to sin I by sin R, sin 90 is 1, is under root of 1 minus 81, n is n max, by FMUF square. This implies sin square I is equal to one minus 81 n max by FMUF square. implies 1 minus sine square I is equal to (81 n max by FMU of square). Cos square I is (81 n max by FMU of square). But we know the derivation for FC. FC is 9 root n max. So 81 n max, FC square is 81 n max, cos square I is FC square by FMU of square, cos I is FC by FMU of secant I 1 by cos I is FMU of by FC. From this, the formula for maximum usable frequency is FMU of is equal to FC into secant I. Clear? This is called secant law. This is called secant law. FMEF is equal to FC into secant I. Is it clear? So if you try to analyze the secant law, if you go for secant 0, how much will be secant 0? Cos 0 is 1. Secant 0 is 1. Secant 90, cos 90 is 0, secant 90 is infinity. It is very clear that for whatever projected incident angle that is possible, 0 to 90, the value of secant will be from 1 to infinity, always greater than 1. Now if you take case 1, the incident angle is 0 degrees, secant 0 is 1, FMEF is equal to FC. That means what? When incident angle is 0, incident angle is 0 means what? Vertical incidence. when incident angle is 0, incident angle is 0 means what? Vertical incidence. At vertical incidence, maximum usable frequency is equal to critical frequency. That's the reason why I said that the critical frequency is the maximum frequency that can be reflected back by the ionosphere. Yet what? Yet vertical incidence. Now you listen carefully. Now slowly things will fall in place. Listen carefully. If you can see here, for critical frequency, I said that the critical frequency is the maximum frequency that can be reflected back by the ionosphere at vertical incidence. Vertical incidence means incident angle is 0. Now I am trying to justify that. When incident angle is 0, Fc, the critical frequency, must be the maximum frequency that can be reflected back by the ionosphere, which is maximum usable frequency. That means FMEF and Fc must be equal when incident angle is 0, and you are getting the same result here. FMEF will be equal to Fc when incident angle is 0. That means at vertical incidence, when incident angle is 0, both FMEF and Fc are same. Is it clear? Is it clear? Now, case 2. The incident angle is not equal to 0. FMEF is equal to Fc into secant I. When incident angle is not equal to 0, at all the other times it is greater than 1. The secant I will always hold a value greater than 1. That means you can say FMEF is always greater than Fc when incident angle is not equal to 0. So what can I say? The critical frequency when incident angle is not equal to 0, the critical frequency is the minimum frequency that can be reflected back. Is it clear? So what can I say? What can I say is, when incident angle is not equal to 0, the critical frequency is the minimum frequency that can be reflected back by the ionosphere. That's the reason why we got this formula here. It is the minimum frequency that can be reflected back by the ionosphere at a non-vertical incident, or when incident angle is not equal to 0. That's why both terms maximum and minimum are used in the definition of critical frequency. Most of the students get confused here. Sometimes people say maximum, sometimes people say minimum. Why it is so? So I am trying to justify that, okay? So now, can I say FMEF is always greater than Fc? Yes, of course. Now the point is, FMEF is greater than Fc by what value? By secant I. That's why it is called secant law. FMEF is always greater than Fc, but by what factor? That is decided by secant I. That's why this law is called secant law. Is it clear, everyone? Okay. So now, if you consider an F layer, For F layer, the maximum incident angle for which the wave will be reflected back is found to be 74 degrees. I'll explain. Let me take a new page. See here. Let me explain here. This is the Earth surface. These are ionospheric layers. This is a D layer. In the D region between 50 to 90 kilometers. E layer. (90 to 140 kilometers). F layer between 140 to 400 kilometers. What I'm trying to tell you here is the maximum incident angle for which the wave is reflecting back from the F layer is got to be 74 degrees. It's got to be 74 degrees. If you further bend, for example like this, the wave will not come back. Maximum allowed for a given F layer based on the height of the layer is 74 degrees. Got it? So I can say for a F layer, the incident angle value is 74 degrees. If you maintain more than 74, the wave will not come back. Therefore, the maximum usable frequency for F layer FMEF is equal to FC into secant I. Secant 74, do it and tell me. FMEF is equal to FC into secant 74. FMEF is equal to 3.6 times of FC. (3.6 times of FC). Clear? Pardon me, what dear? 1 second. Is it clear? Sorry. Yeah, please let me know. Is that clear so far? So what can I say? For F layer, hello Srikant, good morning. FMEF is 3.6 times of FC. That's the maximum possible value. That's it. Okay. Down. Let me do the derivation. Calculation of maximum usable frequency considering Earth is flat. Consider the Earth is flat. This is the transmitting antenna, receiving antenna. We're considering the Earth is flat, and also we're taking the gradient of ionosphere, very thin gradient. That means we are considering ionosphere as a single line. The wave is hitting like this, and it is coming back. And it is coming back. This is the height. To which it is penetrating. This is ionosphere. This is the Earth surface. Capital D is the distance between the transmitter and receiver. This is D by 2. This is D by 2. You can see this is a right angle triangle over here. Hypotenuse square is side square plus side square. Hypotenuse is under root of side square plus side square. The incident angle the reflected angle. Okay? Fine. Now we know that FMEF is equal to FC into secant I. Here, if you apply cos I, adjacent side by hypotenuse, secant I, hypotenuse by adjacent side. Taking under root h square common, will come out as h. Secant I is h times of under root 1 plus d by 2h whole square by h. The cancel of FMEF is equal to FC into under root of 1 plus d by 2h whole square. The derivation for maximum usable frequency considering Earth is flat. So I can say that we have derived two derivations here. Two formulas for maximum usable frequency. One FMEF is equal to Fc into secant I. Is also famously called as secant law. It determines the factor by which FMEF is greater than Fc. One more that we derived, FMEF is equal to Fc into under root of 1 plus d by 2h whole square. FMEF and Fc relation considering assumption that the earth is flat. Clear? Next, we'll go for least usable frequency. Just like we got maximum usable frequency and their formulas as explained in the previous slide here, it is not possible for us to get formula for least usable frequency. Can anyone tell me why? Just like maximum usable frequency, why can't we get formula for least usable frequency? Yes, dear. Just like maximum usable frequency, it is not possible to get a formula for least usable frequency because the least usable frequency depends on different factors. See, you know the maximum usable frequency that can be reflected back by the ionosphere. But as the frequency, I want to know what is the least limit also. Now, the effect of noise decreases as the frequency increase. On the either side, on the other way, as you're trying to decrease the frequency to understand what is the least frequency that it will allow. What is the least frequency that it will allow? What happens here is, as you're trying to decrease the frequency, effect of noise will increase. At one point, the noise will be very heavy. That the signal to noise ratio will become less than 1. Whenever signal to noise ratio is less than 1, that means noise is greater than signal power, communication is not possible. So thereby it forms a limitation. You cannot decrease your frequency according to your will and wish. As you decrease the frequency, the spatial spreading of energy will increase and the signal will die soon. So that's one more factor that you cannot change or decrease the frequency according to your will. Polarization change caused by Earth's magnetic field. Due to the Earth's magnetic field, there will be a change in polarization. Because of the polarization mismatch, losses will occur. And this loss due to the polarization mismatch increases with the decrease of frequency. So as you are trying to decrease the frequency, this mismatch will become more. or the impact will become more, that again it leads to loss of energy. The process of scattering will become adverse. Due to scattering, energy will decrease, as you know, and this scatter process will become more dominant when the frequency decreases at lower frequencies. The concept of focusing and defocusing caused by Earth's magnetic field will also have a very important role, and also this focusing and defocusing will be due to the change in height ionospheric layer. See dear, as ionospheric layer, as you know, layers have this tendency to change the height. The transmitter, the receiver. For example, let me consider E layer. You have set up a communication between the transmitter and receiver using this E layer. Now that if this E layer is changing its height, as it happens, try to fluctuate the height. Now the communication that you had set up will be disturbed a lot, because the defocus is happening now. Why? The layer is not present here now. The layer is present here. Sorry. The layer is present here. Naturally, now you tell me, is the signal strength same here? Sorry. Is the signal strength same here? Just give me one moment. Just tell me, is the signal strength same? No, am I right? The signal strength is not the same. The signal strength is not the same. This is called defocusing. It's called defocusing. Because amount of signal received is not the same now. It happens because of the variation in the height of the ionospheric layers. This is the point that we are discussing here. And this effect increases with the decrease of frequency. As the frequency decreases, skywave absorption increases. Absorption of skywaves increases. Absorption, you take it for any different reason, that increases. Increase in the atmospheric and man-made noise as frequency decreases. The man-made noise and the atmospheric noise increases as the frequency decreases. So all these factors put together will keep a limit on the least usable frequency. You cannot decrease the frequency according to your will and wish. Is that clear? we'll continue with the skip distance from the next class. In the next class, AMM 15 will continue. I thought to continue, but the health is not cooperating. So it's better for us now to stop now and continue later on. Huh? What do you say? Is that okay? Unacademy provides two paid platforms. One is Plus subscription, other is Iconic subscription. In Plus subscription, you got to have the face time of legendary faculties in the form of live classes, weekly test, structured courses, unlimited access, rank improvement batches and crash courses. And in Iconic, we have a personal coach for one-on-one guidance, dedicated doubt clearing educators to clear your doubts, preparatory study material, study planner, study booster sessions, and personalized test analysis. Whether you are taking for a Plus subscription or an Iconic subscription, I recommend you to go for a no-cost EMI, where the total cost will be divided by number of months. Very much useful for students because we don't try to charge anything extra. The total amount will be simply divided by total number of months and you will pay the exact amount. And moreover, you can use my code GCR10 for both the subscriptions, as it can be Plus or Iconic, to get an extra 10% off. With Iconic subscription, you get a personal coach for one-on-one guidance, giving a 1:1 live mentoring, increasing the chance of getting a top rank. Moreover, you can use my code GCR10 to get extra 10% off. And this Sunday, tomorrow, you can test your knowledge by attempting this GATE Mega Combat, which is a live quiz competition conducted for different branches like mechanical, civil, electrical, EC and CSIT. A separate paper will be designed for each of the branch, with 20 questions will be asked, 60 minutes will be given, and the one who top this particular combat, the people who top this particular combat find an exclusive chance of getting almost a free subscription. And the good thing is 200 lucky participants, irrespective of your performance, will also stand a chance to win all these prizes. And if you're thinking that what would be the price, the fees to attempt this combat, we're not going to charge anything, dear. You can enroll for free by using my code GCR10. As I told you, you can enroll by using the code GCR10, and these are the gifts that you'll be getting once you are one of the 200 lucky participants. So it is also a very good opportunity for you to show your mettle, or also check your knowledge among your peer students, where you actually stand in the All India ratings. The All India mock test for GATE 2022 this Sunday, from January 2nd to January 30, we are conducting this. This Sunday, you have one more chance to compete at All India level and exactly know where you stand. What are your chances of topping GATE 2022? This is also free enrollment. You can enroll for free. You can use the code GCR10. These are the special class features where you have interactive live classes, polls for the learners, raise the hand option. You never miss a class. Once the notification is on, you can download the lecture notes. Once the class is done, you can access anytime and anywhere. And there's a new feature here, Unacademy Ask a Doubt, where you can ask unlimited number of doubts. And in your preferred language, you can get the solution. And it's very, very simple to upload your doubt. So we are here to clear doubts. You can ask your doubts anytime you want. These are the new batches. Foundation batch for GATE 2023 and 2024 electrical. Batch A started 19th of January. Foundation batch GATE 2023 and 2024 for ECE explained bilingual started 19th of January. Evolve GATE 2023 electrical. Evolve GATE 2023 ECE. Ascend GATE 2024 ECE. Ascend GATE 2024 electrical. These are the new batches. Each one of them started on 19th of January. You can enroll into this using the code GCR10. All the best, everyone. And thank you so much for joining the session. A very big thank you from Unacademy and a very big thank you from GATE Conqueror. A very big thank you from myself. Thank you and have a good day.